In this animation, we will review how the structure of the dienophile affects the end product in a Diels-Alder reaction. We'll use the same diene throughout. Let's start by reviewing the cis dienophile. Taking a ball and stick model, let's adjust our perspective of how we're looking at it. Additionally, let's take note of our 4 critical sp2 carbons. There are other sp2 carbons present, but these are the ones that matter for a Diels-Alder reaction. If we now look at the unhybridized p orbitals, we can see how they need to overlap between the two molecules to form new bonds. Once the p orbitals are overlapped, let's reimagine some of these double bonds as the electrons that comprise them. As the electrons move, they are breaking the bonds they were once in to form new bonds. Additionally, notice how the ester groups in the dienophile shift as the electrons are moving. There is a lot going on here at once. Take your time to re-watch this part of the animation to get a full grasp on it. Once the electrons have all finished moving, we can reimagine them as proper bonds. In this state, it's hard to envision this as a 6-membered ring, or who is axial and who is equatorial. So we will shift all the atoms around to better illustrate the cyclohexene that has now been formed. What are the orientations of the esters on the cyclohexane ring? One is equatorial down and the other is axial down. It makes sense that they are both down on the same side because we started with a cis-orientated dienophile. Let's simplify this to present the product as something you might actually write on your exam. Notice how we've used dashed lines to indicate that both ester groups are down. This is very important. It is not enough to indicate that both groups are on the same side. You must also indicate which side they are on. Now we will consider the same reaction using a trans dienophile instead. Again, we will shift our perspective and take note of important sp2 carbons in the molecules. The unhybridized p orbitals overlap, allowing electrons to move to form new bonds while breaking old ones. Notice how the ester groups bend as the electrons move. As with the cis dienophile, take your time to re-watch this section and understand how all these components shift during the reaction. We can now shift our perspective to better see the resultant cyclohexene. Note the orientations of the ester groups. One is axial up and the other is axial down. This agrees with the trans orientation of the starting dienophile. Simplifying the representation of the final product, we can get the following. Note how which substituent has a dash and which substituent has a wedge matters here. Recall how the ester pointed toward the diene had to bend up and out of the way, while the ester pointed away from the diene had to bend down and out of the way. The product should illustrate both the geometry and orientation illustrated in the reactants.